Okay, so Markov chains, mixing times, gambling, and the Ising model. So what are the fruits of our research? They're data sets. So you normally perform regression and explain the trends, but sometimes you can fully use the power of mathematical theory and create a model which answers complex theoretical questions, such as when will drug-resistant bacteria take over our world? These past 10 weeks, I've been studying theoretical mathematics underpinning Markov chain models under Kawada-sensei, who is very hard to find on Google Images. My goal is to understand the Ising model with rigor. It is a hallmark in modern physics, and it's an elegant explanation of how ferromagnetism occurs. So, how the spins of atomic particles behave in a collection. When enough spins align in the same way, there will be a macroscopic magnetic pole. So I mainly worked on this book called Markov Chain Mixing Times, and as it was purely theoretical, the method was just me thinking, and I also held 2-hour seminars every week to students and my professor, and just used theorem proofs. So I'm going to try to explain some now. So Markov chains are a sequence of random events in which the probability of the next state only depends on your current state. So it doesn't matter where you've been, it just matters where you are now. So this is how I would write it in a mathematical way, but we won't go into detail here. So we can use Markov chains to model many things, even Fiona's mood. So state 1, Fiona is happy. State 2, Fiona is so-so. State 3, Fiona is gallant. So this is the transition matrix. If Fiona is happy today, she's happy again tomorrow with a probability of 0.5. She's so-so with probability 0.4, and she's glum with probability 0.1. If she's glum today, she's happy tomorrow with probability 0.2, etc. So if Fiona's coffee drinking habits depend on her mood, we can predict how much money she will spend on coffee, things like this. So another useful Markov chain is coupon collecting. So say that there are n different types of Pokemon, and assume every time I get a new Pokemon, it's equally likely to be any of the n different types. How many Pokemon do I need to collect before I catch them all? These are important questions that we can answer. So I proved that the expected number of tau, which is the number of Pokemon I have before I have one of each set, is likely to be this expression. So if there are 10 different types of Pokemon, I'm going to need 30 Pokemon before I have one of each type. I also proved that the probability that the expected number for tau is much greater than tau is pretty small. So by the time I have 30 Pokemon, it's very likely that I have one of each type. So two other important concepts that I'll introduce are the stationary distribution and mixing times. So once the Markov chain reaches the stationary distribution, the transition probability is no longer changed. So it is essentially like a long-run distribution of events. Unfortunately, usually it takes a Markov chain an infinite amount of time to reach the stationary distribution. So we use mixing times to judge when the chain is within a good amount of error of the stationary distribution. So I also did a lot of things for Markov chains on hypercubes, drunken random walks, such as this one, toruses, which are like donut shapes, and trees, and I learned a lot of techniques for calculating mixing times and stationary distributions. So finally we can talk about the Ising model. Okay, so the Ising model places spins up or down on the vertices of graphs to mimic the atomic structure. In one step of the Markov chain, we choose one point at random on the graph, and we allow it to change and keep every other point fixed until the next step. So we let it change under the Boltzmann distribution, which is exponential in negative energy divided by temperature. So if we pick a point which is surrounded by spin ups, then it is very likely to turn to spin up because this will lower the energy and hence it has a high probability of occurring. However, if the temperature is high, then it doesn't matter as much about the neighbors because this is what the Boltzmann distribution tells us, which is a very known theory in statistical thermodynamics. So this is all described by the transition matrix for the Ising model, which is up here. So we have exponent terms, beta is 1 divided by temperature. So So now that we understand the transition matrix, we researched the mixing times for an Ising model. So this is theorem 15.1, one of the final theorems of my studies. So the result states that at high temperatures, mixing time is very short. So interestingly, I actually used the Pokemon collector to aid the proof of this theorem. So in the same way we need to catch one of each Pokemon, we need to select one of each vertice for all of the vertices to become well mixed. So this is quite a non-trivial result actually. So things in physics intuitively happen quite smoothly or linearly. However, this tells us that there is there's almost a phase transition that occurs at high temperatures when materials become immediately non-magnetized because the mixing time is so fast. So yeah, ultimately this is like the end of my talk. At the end of my time at Tokyo Tech, I've achieved the capacity to understand the basics of the Ising model, which is a tenet in modern physics. I also learned how to present 2-hour seminars every business week explaining the theorem proofs that I learned. And I gained skills to further mathematical modeling with Markov chains. Thank you so much for Kawada Sensei's help and guidance and for sitting through all my 2-hour weekly seminars and for the program for organising such a fun experience for me. Thank you.
Do you have any comment? Any questions?